Okay, hello everyone. Welcome back to our computer vision class. So far, we learned the meaning of using the filtration or the filters, and we understand exactly what is the filter and why do we need it. Okay, and up to the moment, we learned two types of filters. The first one is the mean filter, which is the boxy filter, which has all the components or the value inside the filter equal. In this case, it's symmetric on both x-axis and y-axis. And the other one is the Gaussian filter. And for those two types of filter, we said what are the conditions that can be that has to be satisfied for the filter to be considered one of those category of mean filters. There are two conditions we stated last time. What is it? This is one of the conditions, yes. So the summation of all the elements inside the filter must be one, which is exactly similar to the area under the curve. So we assume that this is a 2D, so 3D curve with Z is the value here, and X and Y. Actually, this is Y, and this is X. Okay, so multiplying X times Y will give Z. So if we assume that those are X and Y, and the other values here are the Z values, so we are considering this is a 2D or 3D curve, and the area under this curve must equal 1. Okay? So this is the second condition, one of the conditions. So the sum of all filter component value must equal to 1. Okay? What is the other condition? The size of the filter must be odd, can't be even. So it should be 3 by 3, 5 by 5, 7 by 7, 9 by 9. It can't be an even number. Okay? So if the filter or the kernel satisfy these two conditions, we're considering this kernel or this filter as a mean filter, meaning it's removing the high frequency components of the image. And now we are now understand what is the meaning of the high frequency components and what is the meaning of the low pass filtering. Now, as we stated before, the high frequency components are what? For a given image. So if I have image, specific type, what are the high frequency components and what are the low frequency components?
Those are the dark areas that the dark areas of the image was that high.
Okay. Anything that has abrupt change in data or in signal, we are considering this a high frequency part. Meaning, if you recall from last week, let me open the presentation of last week. here. What are the components that has been messed from here to here? Here we said that we applied low pass filter or anti-aliasing filter to move from here to here. Okay? What are the components we missed? What exactly did we remove?
Those frequency,
Those
the line.
lines. So here, as an example, another one, which we used, this low frequency one. What exactly did we lose? So this is, as we said, is low pass filter. Right? We agree over this last time. So it removed some components from the image. What did we lose?
Pixel.
No, the same number of pixels. The output have the same number of pixels at the end. We are losing edges. The edges, okay? So if you look here, I can easily find the difference between this and this. Here, they become to be more smooth. The edge, the abrupt change that occur in my data disappear. It become more smooth. Okay? Same here. If you look to the example, this one has a smooth transition, right? This one has a sudden abrupt changes here, which are edges. Okay? So the high frequency components of the images are what? The edges. Okay? So applying anti-aliasing filter is removing the edges. Okay? Now the question is, can we detect those edges? Can we capture them only? Here, we learn how to remove them. Get rid of those edges. We don't want them. Now, assuming that I'm having picture, scene, can I detect those edges only? That's exactly what we want to, the question that we want to handle today. Okay? So, our goal for this lecture to learn how we can detect the edges in a given image. Okay? Which is against what we did last week. Last week, we learned how to get rid of those edges and make the image more smooth. Here, I want to learn how to detect those edges. The question that we should ask ourselves in this case, why? Why do I need the edges? Last week, I told you edges are not good and they are causing problem and we need to get rid of them. And this week, I'm telling you, try to detect those edges. Does this make sense? I'm telling you something last week and this week another thing. Does this make sense? The answer is edges are not similar. We have different level of edges. Okay? For example, I'm taking an image for this scene, only this part. Okay? So this barrier between the two colors in the wall will be considered an edge. This surface for the table, these edges, both are edges. Okay? Those considered to be useful edges. Why? Because those edges can describe the scene. So for example, if I told you, describe this bench, how you will describe it? You will say it's a rectangle that has 4 edges like this, and it has legs. So that's how we can describe this bench, right? So I can describe the object using those edges. But what if you look here, you see this wood texture? Those texture are edges or no? Those textures that I have here in the wood. Look here. Those textures are edges or no?
Yes.
They are edges. Are they useful? No. So some edges can be useful because I can use them to describe the objects, and some edges can be non-useful in this case. They are useful in another case. If I asked you what is the material used to build the table? In this case, those textures will be helpful. Okay? But in describing the table itself, it may not be useful. So edges have levels. Some of them can be useful in some case, another can be useful in another case. So not all the edges are useful in all times. And that's what we'll learn by the end of the lecture today. We can adjust the level of the detection to move some edges and keep the strong edges that we need in the recognition process. So edge detection considered to be the first step in any or in most object detection or object recognition process, because the shape of the object can determine what type of this object. Okay? Now we understand why the edges are important. Now the question is, how can I do that? How I can detect those edges? They said, okay, let's go back a little bit to the 1D image again. Sorry, 1D data again. So assume that you have, this is T, and this is X. And this is a signal. Where is the edge here? Can we define the edge? So the value of the signal here over time equals 0 for a long time, 0, 0, 0, 0, 0, 0, 0. Then here it becomes, let's say 10. Where is the edge?
So
On 10.
the above change.
You said
On 10.
the place where you have abrupt change. It's not this, no.
Okay.
And it's not this, no.
Okay.
The abrupt change spot, this spot, because we are moving from level to another. Look here. This is level and this is another level. So this is edge. Look here. Level and another level, edge. Any change from one level to another level with an abrupt change, this can be considered as edge. Now, we defined the edge mathematically. How can we detect this area in a given signal? Let's go back to calculus. If I give you a signal like this, how I can detect this sudden change? The answer is by taking the first derivative. The derivative of this area or this line should be what? 0. Do you see any changes here? By definition, the derivative is rate of change. Okay? So do you see any changes here? So the derivative of x with respect to t here is 0. What about here? in this part. Again, no change here. The signal is too steady. So dx by dt also 0. So the only place that has change is at this part. So if I take the first derivative of the signal, this first derivative can give me an indication for that. So if it will have the highest value or the maximum value, and this maximum value will be the position of the edge. Is there any other place or another indication? Yes. So first, dx by dt will equal some constant value, let's say c. Because here it's 0, here it's 0. Only at this place I will have the derivative. So if you look to the first derivative, actually, it will look like this. Exactly at this time point has value 0 before, 0 after. Okay? Now, what if I take the second derivative for this signal? What is the second derivative of this? What is the second derivative of, what is the derivative of C? Derivative of constant.
1, 0, 0.
0. Constant, second derivative is 0. So the second derivative of this edge signal must be completely 0. And the second derivative of, the derivative of this first derivative will be 0. So I can do two things. First, find the first derivative and, calculate the first derivative and find the maximum within this first derivative. This is the place of my edge. Or find the second derivative and search for the zeros of the second derivative. Either this or this. Okay? Straightforward. You have any problem? No. We are good and we can apply to the image right now. Right? Unfortunately, that's not how we receive the signals in real life. And how we receive the signals in real life. That's how we receive it. The signals are noisy. Instead of a steady 0 and steady 1 or steady 10, it's noisy. In this case, if you try by any chance to take the first derivative, that's what you will get. Can you find the maximum here? Actually, if you found the maximum here, you can get the PhD. It's impossible. Okay? So the signal here is completely noisy. Okay? So finding the maximum value according to this derivative considered to be impossible. How can I solve this? We should get rid of this noise, right? Those noise are high frequencies or low frequencies? What? Those are edges, right? But they are noise in my signal. So high or low? Low. Those edges or no?
Yes, sir.
We said the edges are what?
About change.
Right, but are the edges high frequency or low frequency? High frequencies. So those are high frequency components that we don't need. That's why they are noise, right? So I need to get rid of those high frequency components that consider to be noise for me. How we can get rid of the high frequency components? We learned this last week, right? Using what? Come on. Gaussian filter.
Gaussian.
So if we apply Gaussian filter over this signal, it will smooth it and we will get rid of those noisy high frequency components. So this is the signal. And this is my Gaussian filter. If I convolute or apply this filter to the signal, this will be the output. As you can see, the Gaussian filter make the signal smooth. I'm good, right? No, I'm not good. Why? Because this is low pass filter. Yes, it removed those noisy signal, but it removed the abrupt change that I have. The abrupt change become what? Smooth. So now I need to find the first derivative again, but the first derivative in this case will not be as sharp as this. You see this? It was completely sharp. Now the first derivative is not sharp. But still, the maximum value of the first derivative is the edge position. So I still can find the first derivative and search for the maximum for the, excuse me, find the first derivative and search for the maximum for the edge position. Okay? Any problem so far? So, have the signal convoluted with the Gaussian filter. Which will work as a low pass filter to remove those noise. Then I will take the derivative of this convoluted signal. Okay? Now, one of the properties of the convolution is if I'm taking the derivative of two signals convoluted to each other, I can introduce this derivative inside to only one of them, which means that I can find the derivative of the I, then convoluted with G, or find the derivative of the G, then convoluted with the I. Either way. So this equal this equal this. Okay? I think we already saw the derivative of I, how it looks like, right? This is the derivative of I, and how it looks like. Is this something I want to do? No. So instead of calculating this, I will take the derivative of G directly because it's my kernel and it's fixed. So I can calculate the derivative one time and apply it to any signal that I receive. Okay? Now, what is the derivative of this Gaussian filter? If we try to take the derivative of the Gaussian filter, that's how it will look like. Divide into two parts, part up and part down. Positive part and negative part. So the area under the Gaussian curve equal what? What is the sum of the area here? The area under the Gaussian curve equal what? 1, right? Because it's a PDF, probability density function. So the area under the curve is 1. Now, how about the derivative? The area under the curve here equal what? The area will equal what?
minus
one over the axis and one under the axis. So the area will be 0. Okay. So the derivative of the Gaussian will have an area under the curve of 0. The positive area will cancel the negative part, and the total will be completely 0, rather than the Gaussian itself. The effect of this derivative over the signal will be exactly as if I apply the signal first, then I take the derivative. No difference. But the only difference that this one I can calculate once and will keep it and apply it to any signal I want. So I don't have to find the derivative of any given signal. So this will reduce our computational complexity. Okay? Remember, when we were discussing this, I said also that I can get the second derivative and let it equal 0. Can I apply the concept of the second derivative here also? So instead of getting the second derivative, I take the second derivative of g, then apply to the signal? The answer is yes. And this is the shape of the second derivative of the Gaussian. Okay? The second derivative operator called Laplacian. Laplacian operator, which is second derivative over the independent variable. And the core filter that we are using here is a Gaussian filter. That's why this second derivative called Laplacian of Gaussian, which is a very well-known filter or operator that we will use a lot later. So we are using the Gaussian by itself as a low-pass filter. We are using the first derivative of Gaussian for edge detection. And we still can use the second order of Gaussian also for edge detection at the cross point. According to the concept we introduce here, the second order of the derivative will be 0 at the edge. So instead of searching for the maximum, for the first derivative, I will search for the cross point, the transition from positive to negative. This will be the edge position. Okay? So now we have several techniques to find the edges for a given signal. So this is good for the one-dimensional data. Can we apply this for the image? They said yes. So we will replace the traditional Gaussian filter with 2D Gaussian filter. The equation for the 2D Gaussian filter, and the general equation for the 2D Gaussian filter is this: 1 over 2 pi determinant of s power half e power 1 over half xy times s inverse times xy. The s is considered to be the covariance matrix. So this is which find the relation or the covariance between the x and the y axes. In most cases, those covariance between x and y are zeros, which means that the x axis is completely independent from the y. In this case, those will be 0, and this and this will be sigma square, and they are equal. And the equation can be simplified to this value. So this is the general equation for 2D Gaussian. For 1D, I think I wrote it last time. Can someone recall it for me? What is the 1D equation for the Gaussian? This one. Nothing? I leave it for you to check from last lecture. Okay? So, if you try to plot the 2D Gaussian filter, that's how it will look like. Okay? Again, it's a bell shape. It's not regular normal. And the area under the curve still 1. So the area under the curve will never change. It will still 1 forever. Okay? Now, here we have two axes, x and y. We go here, we'll see that we got the derivative with respect to x because we only have x in this direction. Right? Do we have only x in this direction? No, we have x and y. This means that I need to have two derivatives. A derivative with respect to x and another derivative with respect to y. The two derivatives actually are similar. The only difference between them that they are rotated. Okay? So if you calculate the derivative with respect to x, that's how it will look like. If you calculate it with respect to y, it's exactly as if you rotated 90 degrees. So the shape of the two derivative, that's how it looks like. This is derivative with respect to x. This is the derivative with respect to y. Again, the angle for both of them if you try to visualize this graph, that's how it will look like. White for the positive, black for the negative. And in between, it's grayish. Okay? This one is exactly similar, but only rotated. Now, the question should be, what is the dimension of this filter? Is it fixed? Like every time I want to calculate Gaussian filter, I will use a specific number of points of M and N, or there is a criteria or a technique we can use to calculate those M and N. Actually, I mentioned this last week as well. Anyone remember? Anybody recall? There will be 5 points bonus. As I stated last time, the rule of the fixed sigma, the area under the normal distribution can be covered almost 99.7% of it if you go three value of the sigma in this direction and 3 value of the sigma from this direction, which make the total width from here to here equal 6 sigma. So the filter size must be bigger than the value of the 6 sigma. So for each signal, this one has sigma value. So this filter size must be bigger with 6 sigma. And in most cases, they are equal. To make sure that all the power of the filter included inside here. Okay? So if you apply, assume sigma equal 1. Okay? In this case, 6 sigma will equal 6. Can I apply filter 3 by 3? Can I choose Gaussian filter of size 3 by 3 for this sigma equal 1? Can those be compatible with each other? Why?
The time is different, right? Here is 3, here is 1. It should be 3 by 3. Same size.
N equal M equal 3. And the sigma equal 1. Is this a valid filter? Let's see. Sigma equal 1. Then 6 sigma equal what? M greater than 6? Then this is not a valid filter. If I choose M equal 5 for the same sigma, is this a valid filter? Why? Again, this is 6 and this is 5, so this is smaller, so it's not a valid filter. If I told you that M equal N equal 9 and the sigma is 1, is this a valid filter? Yes, because the value of M and N now is bigger than the 6 sigma. Then this is a good filter. So choosing the filter size should be proportional or function to my sigma value. Smaller sigma should have a good or proportional value. Increase the sigma, you have to increase the filter size to satisfy the 6 sigma rule. Okay? Is it clear? Okay. Now, the question, this filter is good and more practical, and we can easily find it or calculate it on the computer. But do we apply a continuous value to the image or discrete? Like the filter that we choose for the low pass. It has discrete values, right? It's not continuous, it's not function, right? Now, can I approximate this into digital or discrete values? Actually, there are so many trials to do that. One of them is this trial. So this said, let's look to this filter. This white area I said is what? Positive. And this black area is negative, according to this definition. So I will represent this with 1, represent this with -1, and we'll have an even filter. Remember in the average filter, we said what is the condition for the size? It's just at the beginning of the lecture. Exactly. Do we have the same condition here? No. So this one is even, it's not odd. And the sum of the pixel value here, or the value here is what? 0. Okay? For the y, I said we rotated 90 degrees, right? So rotated 90 degrees. Simple. If you rotate this 90 degrees, you will get the derivative or the value of the filter with respect to the y. Now, if we apply this to the image, what we will receive? So assume that we have this image and we'll apply this convolutional filter to it. So this is a filter. I'm doing convolution process. Okay? Can you tell me how to do the convolution of that? Yes. How am I applying the convolution filter or the kernel to the image? Okay. So please close your computer and focus with us, okay? So we will apply it using the traditional convolutional mechanism. So this is my x, this is my y, and I will apply the filter in this location on the top left corner, multiply each pixel here times the corresponding pixel here and sum, and add it to the result. Shift, do the same thing. Shift, do the same thing. And I'll keep doing this in all the x. Then shift back down and do the same thing as we learned from the last convolutional process. Okay? Same thing with the y1. So I will add the filter like this, vertically rather than horizontally, and we'll find the difference like this. Now, can you look to both of them and tell me which edges is clear here and which edges are clear here? The original image has lots of edges. So which edges clear in this one and which edges are clear in this one? Okay, let's focus on this. Which edges are clear? Vertical edges, right? Why? Because the filter itself is horizontal. Here, the horizontal edges are more clear. Why? Because the filter is vertical. Okay? So this will be the rule for both of them. If I found the derivative with respect to x, I'm focusing or producing vertical edges. If I found the derivative with respect to y, in this case, I'm finding the horizontal edges. Can I combine both of them and find all the edges? They said yes, using the magnitude concept. What is the magnitude concept? Using the square root, the square of this value plus the square of this value, add them together and get the square root, then the modulus. I will receive or have this one, which will be a full derivative. So this one is the derivative with respect to x. This one is the derivative with respect to y. This is the full derivative. Okay? What we found here is what is a magnitude. What is the opposite of magnitude? When we have a vector, then we have magnitude and. So we found magnitude. This means there is what? There is an angle or direction. How we can find the direction and magnitude of the vector? Inverse of sy over sx. So the output of this technique should produce two things. magnitude of the derivative and the angle of derivative or direction of derivative. Okay? Both of them are outcomes for my calculations. Okay? After that, some people say this is not good for two reasons. First, this even number of pixels or filter will get me confused. If I add this and subtract it from this, then I will put it here in which position? In this position or in this position? Confused, right? So it's better to make this odd as well. Is it mandatory? No. But it's to reduce the confusion. Second, look here. Here is positive, here is negative, right? But in between here we have what? Exactly. It has a zero area, zero crossing parts. So why should we keep this like this? Or like, why should we keep it like this without the zero in the middle? Let's add zero in the middle. That's why we had those three trials. This one said we will add zero in the middle, and here is full ones, and here is full zeros, sorry, full minus ones, and it will be 3 by 3. And this is the rotated version as we stated before. This one said I will do it diagonally. So 1 here, minus 1 here, and 0 here, and here is the opposite. This one said this is not accurate and this is not accurate. Why? Because if you look here, it's not all with the same value. So it doesn't make sense to keep all of them positive with the same value. I have to make them positive, but with a B. Then smaller value. Peak with the smaller values. So I will make a peak here in the middle, lower on the two sides. Peak in the middle, lower on the two sides, and 0 in the middle, which produce this one. The names of this middle filter is a Sobel filter, which is considered to be one of the canonical techniques we can use for the edge detection. Okay? This Brewitt filter and Rupert's filter are okay, they are not bad, but they are not considered to be a good approximation for the original Gaussian derivative. The Sobel is the best approximation to the, excuse me, the best approximation for Gaussian derivative function. Okay? Now, the best question here is, will we always use the 3 by 3? Or we can use other dimensions? Then we have 5 by 5. Can we have 7 by 7?
Yeah. Yes.
Actually, yes. So there are versions of Sobel filters which have higher dimension value. So there is Sobel 5 by 5, there is Sobel 7 by 7, there is Sobel 9 by 9, and higher. But in most cases, 3 by 3 is the one mostly used. Okay?
So when it gets bigger though, do you keep putting zeros in the middle?
Okay. In this case, it will go gradually to 0. Actually, it's included in the next assignment, and I will show it to you after we finish. So in this case, we start with a bigger value in the middle and go gradually for both sides, then 0, then gradually for the other side.
Zero is gonna stay
In the middle.
one lane.
Yes.
Okay.
Okay. So the best actually approximation to the Gaussian using the Sobel operator has 1/8 before it. This is the best approximation. Okay? But do we always use it? The answer is no. So practically, we don't need to use this term in most cases, but sometimes we use it to calculate accurate gradient. So calculating the magnitude accurately will let us include this 1/8. But it doesn't make that difference to include it in the shape of our gradient. Okay? Now, how this Sobel operator will look like? Again, if we assume that this is the original image, we can calculate those two operators for the image. So can you tell me which one of them the derivative with respect to x and which one the derivative with respect to y?
X and Y.
Yes. Well, this is number one to this, and this is number two. Number one and number two is with respect to x.
Or Y is equal to X.
Why? Yes. Okay, so welcome to engineering of guessing. One or two?
Two.
Who is X?
So I'm using as well.
Which one is x, which one is y?
The one on the left. Oh, okay.
This is x, and this is y. We said x produce what? Vertical. Y produce horizontal. So this is x because it produces vertical lines. And this is y because it produces horizontal lines. So this is okay. So that's how you can determine if your image or your derivative is with respect to x or with respect to y. Not just because this is to the right and this is to the left. No. Okay? So if the derivative or if the edges that you can see is vertically, this means that this derivative is with respect to x. If the edge is mostly horizontal, then this means this is with respect to y. Again, for this, we can calculate two things. First thing is, those considered to be vectors right now. This is the x component of the vector, and this is the y component of the vector. And we said for the vector, we are calculating what? Magnitude and angle. So this is the magnitude, which equal for the angle. Okay. Is it clear? Any problems? Okay. So the question is how this technique is robust against noise. We saw before the main cause of all of this is the noise, right? But all the images we are working on right now, they don't have any noise, right? They are clear. What if the noise starts to be introduced? What will happen? So if this is the clear image and we apply the subtle edge detection, that's what we will receive as a magnitude. We start to add more noise, and this type of noise actually called salt and pepper noise. Okay, it adds white pixels and black pixels in the middle. In this case, if we take the first derivative and start to get the magnitude, that's exactly what you will receive. Now here, the maximum is clear. Do we have a clear maximum here? Not really. Actually, we have thin line or thin area that we need to choose from. Here, it's almost 1 point. Almost. But here, it's an area. It's too thick. So which one of them is the actual difference? Which one of them is the actual edge? Okay? That's why we need to design a technique to find this actual line inside this area. Okay? So using the canny edge detection, the supple edge detection by itself is good if the image is clear. If we have some noise, yes, I can detect the area that has the edge, but it will be an area, not only one line or 1 point, and it will be blurry edge. So we need to define or find the criteria to solve this mystery. Okay? Now, so far, if I give you a filter, can you identify this filter if it's a derivative filter or an average or smoothing filter? Now I can give you a random filter, write a random filter now on the board. Can you tell me or identify if this filter is a smoothing filter or a derivative filter? Again, we have to check the properties for both of them. The properties for the smoothing filter is the values always in the Gaussian filter or the block filter or the box filter. In both cases, we don't have any negative value inside the filter. Second, the sum is always 1. Area under the curve, always 1. The amount of information proportional to the mask size, and the mask size is always up to n plus 1. This is odd number. Okay. How about the derivative filter? It always has opposite signs of the filter. So one size positive, one size negative, one size positive, one size negative. They are not always positive or always negative. As a result, the sum is always 0. It will give you high absolute value at the point of high contrast or the point of change, as we saw, which is the definition of the edge. Okay? So that's how we can distinguish or differentiate between the smoothing filter and the derivative filter. Now the question is, can we use the filter of derivative by itself for the edges? The answer was no, because of this problem. So what exactly we need to do to fix this problem? We will go through a protocol. This protocol will be our algorithm for the edge detection. What is this protocol saying? First, I will find the gradient of the smoothed image in both directions. What is the meaning of gradient of smooth image? Smoothing means apply Gaussian filter. Find the gradient means find the derivative. So the gradient of Gaussian filter. So I will find the derivative of Gaussian, which is whatever we calculated right now, or we cover right now using Supple filter for X or Y, depending on whatever you are doing. Then convolute this with our image. That will give us 2 derivatives. X and SY. Then I'll calculate the magnitude of this gradient using the equation already. And also I'll calculate the angle for that. Calculating this makes sense. Why do I need the angle? Why the angle is important for me right now? This one makes sense because this is the shape of the edge that I'm looking for. The angle will make any difference here.
Yeah.
Direction of what?
To the right.
Actually, that it'll tell you like where it is exactly.
Actually, it shows you the direction to the edge, right? So the angle will point to the edge. Okay? So if I look to this one as an example, you will see the derivative here pointing to this one. The derivative here pointing to this one, which means that this in the middle is the maximum. That's why this angle is important for me, because it shows me where exactly I should go. This exactly, or this technique of looking, this technique of using the derivative, the angle of the derivative to find the maximum position is called non-maxima suppression. We'll go through it in details in a moment. So this concept, use the angle of the magnitude or the derivative to direct it or direct your algorithm toward this maximum if you have a cloud of points. Okay? After that, after I use this non-maximum suppression, I will do thresholding, which means the point that has derivative higher than specific threshold, those will be considered as edge. If it's lower than the threshold, ignore them. Okay? And this algorithm actually will be called canny edge detection. So this technique is the canny edge detection algorithm. So the algorithm saying, first, find the derivative with respect to x using the derivative of the Gaussian filter on both x and y direction. Then calculate the magnitude of this derivative. Then calculate the theta. Then use this theta to guide you toward the point of maximum derivative. Then for those maximum derivative values, apply threshold to them. The output from that will be your edges. Okay? Very straightforward. 1, 2, and 3. Okay? So we'll start by having the image. This is sample for the image. Okay? Then we will apply the derivative with respect to x and the derivative with respect to y. Then we will find the magnitude, which is this one. As you can see, it's so clear that this is not one point, it's a cloud. So this one had a width, you see, maybe about 10 pixels or 20 pixels, this edge. Okay, so we can't ignore this part. When we are saying edge, we are saying 1 pixel. This is the edge that we are looking for. Okay, not a band of 20 pixels or 50 pixels, no. So after we calculate this, we will start to calculate the direction. Now, note that I am at specific point B, which is inside this cloud. Okay? And the derivative here has a value. Let's say 3. I want to see if this is the maximum one or there are more maximum around me. Where I should search? They said search in the direction of the theta. This theta. The direction of this theta will tell you if there is more maximum or no. So I will check the theta and will search in this direction. This will fall me into a trap. What is this trap? The theta value is continuous, right? Meaning it can be 0, 1, 2, half, 3, any number, right? Does all those values lie in my image? The answer is no. If I'm here right now and I have the derivative, my neighbors, one in this direction, which is of angle, here, 0. I have one of this direction, which is of angle, 45. One in this direction, which is of angle, 90. 135, 180, whatever. So 180 plus 45, 270, 360 minus 45, and I return back to this one. Those are the value I have. What if I got theta equal 10? What should I do? What exactly I will search? Theta equal 10 means it here. Is there anything here that I can help me with the search? No. That's why we need to do approximation a little bit. What is this approximation? This said, I can consider a cone of width 22.5. Why 22.5? Because the sum of those is 45. So 22.5 up, 22.5 down will make what? 45 degrees. Okay? So within this range, I can consider any value of theta will produce this one. Again, for the same for that. So 22.5 here, 22.5 here will produce that. Same for that, and so on. So this way I can approximate. If any theta come within this, I will search for that. If any theta come within this, search for that, and so on. This is the technique. Another technique said, this is not good. If the theta is 10, I want to search for 10. I can bring the 10 for you. Do you have any value of the 10 direction? No. How we can solve it? They said interpolate. Remember the interpolation technique we used for the super resolution? We will interpolate here as well. So the value at this direction that we don't know or we don't have value equal portion from here times alpha plus portion from here times alpha minus 1. Interpolate them. So you can calculate this value as an interpolation between the two values. So those are the two techniques that can be used for the non-maximum suppression. Again, what is the meaning of non-maximum suppression? I'm calculating the theta, the angle of each derivative, and I'm searching in this direction of the angle for any maximum value. If I found maximum value in this direction, then the new maximum value will be the maximum value. Okay? The problem or the challenge in this part is the value of the thetas are discrete. I have at 0, I have at 45, 90, and so on. I don't have anything in between. How can I overcome this problem? Using two techniques. First technique, approximating any value within a cone of 22.5 to be the value in the middle. This is the first technique. Second technique, interpolate. Is it clear? So, the this non-maximum suppression, I will receive something like this, which will drop some pixels. After that, I will do thresholding. What does the thresholding mean? If statement. If the value of the derivative survived from the non-maximum suppression greater than specific threshold, the output will be 1. The output will be 0. This will produce this image, which is an edge image. What are the properties of this edge image? First, it has the same size of the original image. So if the other one m by n, this is also m by n. Exactly the same size, no change. Second, it's a binary image. What does this mean? The pixel values here are either 0 or 1. 0, not age, 1 is age. So does this mean that I don't have any 255 or any value in between? No. 0 or 1. Okay? So it's a table filled of just zeros and ones. No other values. So this is binary image. So watch out, because many students and many users, when they produce or when they have an edge image, they use it for other application, considering the value here 0 or from 0 to 55 or grayscale. The answer is no. This is not a grayscale image. This is binary. Okay? Now the question is, can I control the edges that I can receive here, or it's not changeable? Once I receive edge, it's fixed. I can't adjust it or remove part of it or show more or anything. Is there any way to adjust it? Let's see. So let's have another example. Within this example, I want you to think. So assume that we have this image, okay? Again, we will apply the protocol we discussed. First, I will find the derivative with respect to x and with respect to y and calculate the magnitude. Okay, as you can see, the magnitude show you a cloud. Okay, there is no specific value for the edge. Then I will calculate the orientation or theta. Okay, so the theta also is an image or a matrix. Okay, because some of you may think this is only value, vector of values. No, it's an actual matrix. Then I will use the non-maximum suppression. Okay, so using the technique we described, I'll try to use the direction of the derivative to guide me toward the direction or the value of the maximum in this cloud. Then, see, so this is before the non-maximum suppression, and this is after the non-maximum suppression. You see what difference? But is it binary now?
Yes.
No. Before thresholding, still not binary. Okay? We just removed part of the cloud. Okay? Now, excuse me. You want to show some of the weak edges or some of the edges on the background. Now, those edges are really strong. You see how strong they are? Very white. Those are edges, but weak. And on the back, you have many edges, but as you can see, they are weak. They are not strong. Okay? Now, if we apply the regular thresholding, what will happen is we will show those strong ones and those weak will disappear. Can we tweak it a little bit to make it flexible to show the weak and strong? They said yes. We will do a small trick. What is this trick? We will add one extra threshold. We are calling it lower threshold. So we will have two thresholds, lower and upper. Before, we use the upper only. If it's more than that, it's an edge. If it's lower than that, it's not an edge. Now we said we will add one extra threshold. If the value above this higher threshold, then it's edge no matter what. No one can complain. It's an edge. It's between those two, it may be edge or maybe not. So here, maybe. Here, for sure. Here, maybe. If it's lower, not edge at all. Okay, so now we have two decisions has been considered. The for sure and not edge. What if this may be? How we can solve it? They said we will use a small tweak. If this maybe is connected to a for sure one, then it's an edge. If it's not connected to anything, then it's not an edge. So if this value is bigger than this higher threshold, it's a strong edge. If it's between the higher and the lower threshold, I will consider it as a weak edge. In this case, I will check its connectivity with other parts. This checking of connectivity, we are calling it hysteresis. Okay? If it's lower than this lower threshold, then it's not edge at all. Okay? This way, I can control more the number of edges I can receive in edge. By adjusting this T capital and T small, I can control the number of edges I can receive. So here is the output, the final output. As you can see, if I have higher value T small, I'm ignoring those at all, completely ignore. Reduce the value of T small, you will have all those edges. Okay, so it's a strong edge, then it's an absolute edge. If it's a weak edge and it's connected to strong one, I will consider it as an edge. How we can discuss this connectivity? We usually look to the 8 closest points, if there are edges or no. If any of the close point is edge, this will be considered as an edge. If it's lower than the lower threshold, then it's absolutely non-threshold or non-edge, and I will ignore this. So the final algorithm can be considered this way. Filter with the derivative of Gaussian, again, in both direction, Sx and Sy. Then I find the magnitude and the gradient, or theta. Then I will use those to the non-maximum suppression algorithm. Then I will use this weak and strong thresholding technique to find the edge and the connected small edge. So those at the end of the day produce the Kelly edge detector. Okay, which is considered to be one of the most important edge detection algorithm available so far. Okay, it's used a lot in many applications. Okay, now let's take a break, 10 minutes, and after the break, we want to think about other parameters we can tweak in this algorithm to understand or show the weak edge and the strong edge. Actually, let me take the attendance first, then we can go for the break. So far, we learned how the Canny edge detection work using the 4 steps we are applying for the algorithm. And we said that we can adjust the two thresholds, the lower threshold and the higher threshold, to achieve the best performance or the required performance depending on the number of required or the edges we require to count or the edges we want to ignore. Okay. As we said, if this is not the only parameter we can control to find the value or find the required edges. So those two parameters, which is the lower threshold and higher threshold, considered to be one of the important parameters we can choose. But also the value of sigma. Which sigma? Do you have any sigma here? The algorithm we have here. Do you have any sigma? What?
Gaussian.
Exactly. Remember, when we discuss this, we said that based on the value of sigma, we'll choose the filter size and all of this. So this sigma is a parameter to control for the Canny edge detection. How can this be a value? How this can be considered a problem? This said, if I have a higher sigma, this means I'm filtering the image with more smoothing or better smoothing that will make the lower edge or the smaller edge or the weak edge to disappear. So higher sigma means low number of edges. If you increase the sigma value for this derivative filter, you will receive lower number of edges. Smaller sigma means more number of edges. So now we have 2 parameters to play with. Sorry, 3 parameters to play with. Lower threshold, higher threshold, and the sigma value. Those parameters can choose which edges I want to keep and which edges I want to discard. Okay? So I can now fine-tune the Canny edge detection to find any value of my choice. Okay? Now, as you can see, whatever we are doing right now is exactly similar to the convolution process we learned last week, with more operation we are doing on the output of that. Okay? So, all the process we are doing for edges, for smoothing, for filtering for anything end up to be a convolutional filter. Okay, so convolutional filter is an essential tool we have, we have in our computer vision work. So far, we have filter for the box filter can be used for smoothing. I can use bilinear filter for what? What is the function of the bilinear filter? All of them convolution.
Easy.
This is smoothing. This one is what? Super resolution. Interpolation. Okay? So this one I can use for interpolation to have a higher version from a given image. I can have a Gaussian filter for either smoothing or for interpolation as well. Okay? Sobel filter can be used for what? What is the function of the Sobel filter that we learned today? Okay, so it calculates what?
Derivatives.
Exactly. Derivative with respect to x and y. Okay, which we can use to the edges. So watch out, because this is one of the traps many of students fall on. This is the output of the Sobel. Are those edges? Why?
Because radius. Because of we have not done the threshold.
Because this is not binary. It's not a binary image yet. This one has a pixel value from 0 to 255. Yes, it has lots of black areas and lots of white areas that represent the edges, but it's not a binary image, so it's not edge. This is the output of Sobel. Okay, so Sobel is doing the derivative, yes. Is it produce edges? No. Make this clear, okay? And the final one, which is the one we will cover, start to cover or work on tonight or within today's lecture, then we will go through, continue it next week, which is the corner. We can use this convolution also, convolution filter, to find the corner within the image. So we are using filters or convolutional process in many applications. Now the question is the convolution expensive or cheap? Meaning, how many loops I have to go through in programming to do the convolution process, 2D convolution? Translate the word a lot.
Depends on the size.
Okay. Can we have an equation for that?
M multiplies by n.
Let's have an equation. So if you look to the definition of convolution, you will see that you will have to go through all the rows and all the columns. So as a computational complexity, you are working in n by n. Right? Is this a good thing or a bad thing?
And it's bad thing because it's a very long process.
So if I have an image which is 10 by 10, it will take 100 iteration. If I have image 3000 by 3000 will take what? 9 million iteration. Is this a good thing? It's not good. So this is of order n squared. Okay? Something that we don't like. Can we use a more efficient technique to do the convolution process? If we found efficient technique to do this, we can do all our process more efficiently. The answer is yes, I can do some tweak. So if you calculate the number of multiplications and the number of addition that we are doing with the regular convolution process or cross correlation, what's the difference between correlation and convolution?
In convolution, we do cross correlation with inversion.
So convolution is exactly like correlation, but the filter is flipped horizontally and vertically. Okay? That's why all the scanning process is a correlation. Okay? So if you count the number of multiplication process, you will see that you are multiplying every pixel here toward the corresponding pixel in the image. So you have 2n plus 1 square multiplication process. Why 2n plus 1? Why did I say n or m? Why I made the filter of size n by n? Why not? Why 2n plus 1? Why?
One column, because you are doing one column both men.
Why I didn't make the filters of size n by n? Why I make it 2n plus 1?
It must be all.
Must be? Exactly. So this is the representation of the odd number. So if n equals 0, the filter will be 1 by 1. If n equal 1, the filter will be 3 by 3. If n equal 2, it will be 5 by 5, and so on. So the filter, in most cases, or in all cases, is odd size. That's why we represent it by 2n plus 1, not n by n. If I put it n by n, then it can be odd, it can be even, right? But when I make it 2n plus 1, this means it's always odd. Okay? So multiplying each one here, corresponding one here. So I'm doing 2n plus 1 square multiplication operation. Then I will add all of those together, which means I'm doing 2n plus 1 square minus 1 addition operation. So the total number of operation here is n square multiplication, n square addition. Okay? Which is, if you calculate or plot this, to look like this. Okay? Second order algorithm, which is not good. Can we improve this a little bit? They said yes. This filter of size 3 by 3, right? As an example, or 5 by 5, or 9 by 9, or whatever it is. I will divide this into 3 by 1 times 1 by 3 vectors. If I multiply this type this, it will produce this one, right? Row times column produce this. Row times column produce this, and so on. Now, I can apply each one of those separately to the image. Let's see. So, assuming that I'm working with the vertical one. So, it's only this part. So, how many multiplication operation I'm doing right now? Only n plus 1. How many addition operation I'm doing right now? 2n plus 1 minus 1, which is 2n. Then I will repeat it for the second one, which is of the opposite size. this one. That will make the total number of multiplication 2 times 2n plus 1, and for the addition 2 times 2n, which makes 4n. So this will make the convolution of the order 2 times 2n plus 1, and this is 4n. Is there any change from here to here? Do you see any change between this order and this order?
Not square.
Which means become linear. So the curve, instead of being squared curve, it become a linear curve. So it's not growing fast. It grows, yes, but smooth, slow a little bit. Okay? Can I improve it more? They said yes. How about if I take 1/3 from this vector and 1/3 from this vector? So it will be 1/9 times 1 times 1. Okay? Now apply it within this shape. What I will do is no multiplication at all. I'm now selecting. If I multiply anything by 1, are you making multiplication? You are masking. Selecting those pixels only. Okay? So if I select those pixels only and multiply them times 1/9, this means the number of multiplication become what? Only one multiplication process that you are doing. How many addition you will do? Add those together. So it will give me 4n. So this become 1 multiplication and 4n additions. What is the meaning of 1 multiplication?
So the same.
It doesn't matter the size of the image. If the image is 3000 by 3000 or 10 by 10, the time will be similar. Okay? That's why the convolution process or the correlation process can be applied more efficiently to the image if I divided the image into 2 one-dimension segments and treat them each one separately, then produce them back. And that's exactly what we are doing over our computers on our phone. This process, how it's doing. So almost no multiplication. Fixed, 1 multiplication per cycle. Then we will do, then we will do the addition. Okay? So we can now play with the technique of convolution or correlation to make it more efficiently and work better on hardware devices, so we can apply on higher dimension image and for many applications. So any process now I can convert it to convolution. It will be cheap for execution. Okay? Not a big problem for us right now. Any questions so far? Any problem? Okay. Now, I detected the edges. Can the edges by itself help me understand specific scene? Like, look to the scene that we have here. Assume that I detected those edges. I detected those edges. Okay. Can those edges tell me or give me a full story of my given scene?
Yes.
This actually become a debate in the computer vision world. Some people said, yes, edges are good and we can use them for several applications. Others say, no, edges are not good. We need more describable technique or information or information from a given image. They thought a lot about what exactly they can capture from the image that can be more informative. And it ended up with them of two things. One is the corners. The corners that we have in our environment can be considered as a unique information that we can use to identify the scene, or at least understand the scene. Another group said, no, blocks considered to be a more description or a more descriptive for the scene. Like what? Like those light spots, blobs. Those speakers, blobs. This camera, blob. This router. Those spots or those lights, those holes in the chair. All of those considered to be hidden information in my scene that I can use to understand this scene. So the two schools said, if you can extract the corners, we can use them in a way to understand the environment. Another say no, if we extracted the blobs, we will be able to understand the environment. But both of them told those points as points of interest and the points around them as features. So now we want to understand the concept of features. What are the features in a given image? The features are the area surrounding any points of interest. So here, if I check this table, this corner has an area that I can use to identify these objects. Same here, same here, same here, same here, same here, same here. All those corners have information around them that can be used to identify the objects. Okay? So the corner itself is a point of interest. The area around this point of interest considered to be features. Same thing with the blob. I can consider the blob center as my point of interest. And the information around that center is feature as well. Okay? So that I can do many things. What exactly I can do with that? I can use it to build panorama picture. So I can capture image here, capture image here, capture image here, and connect those images together as if I'm seeing them to build a bigger scene. Which is exactly that you have now on your phone. If you open your phone and your camera, you'll find the feature for panorama view, right? What exactly is your panorama view is doing? It will ask you to stay like this and move and don't go up or down, right? Keep moving like this, keeps rotate, 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 and return to the same place again. So what happened is it keep capturing image, 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 then connect them together, seal them together to build the 360 view for the image. So we can do this using this technique. How? While I have those two images. Actually, let me show you. Like this. Those two pictures for the same scene. Can I connect them together to build a panorama? Which is which? Which part should be put on the other? So if you look and focus a little bit, you will see that this part is this part, right? This part is this part. Here, I don't have any other information here to match. Here, I don't have any other information here to match. So I will assume that the information here is similar to here. So I will try to use this to match them to build a bigger scene. So the question is, are they matching 100%? The answer is no. I have to rotate and adjust one of them to match the other. So if you see, this is the original one. You can easily see the border. I rotated it and adjusted a little bit to match the second one. But I can now have a bigger scene. Okay? Is it useful for this application only? The answer is no. I can use it for another thing. What is it? Something called visual slam. What is the visual slam? Assume that you are driving a car and you lost your GPS signal. No GPS. And you want to see or find the path that you followed before. So you started from here and you are driving this way. Okay? You want to draw the path that you already been through. Can you do this using the camera? Yes, using this technique. So I can identify those points on both sides of the road and match them on the next one. When I move, match them on the next one. I move and keep doing that again and again and again. So I can use this to build a path for myself. Actually, let me show you a video for that. While it's open. Okay. Other thing we can use is image matching. Someone give you a scene for some place and you want to see or to understand where is this place. So you can keep search in your data set and find a match between those two scenes. Like this one, as you can see, this is different from this, has been captured in different place, different location, different time and different illumination, but we still can match them together. We can have those hard cases. Like the other two were easy a little bit because the view is just shifted. But these two is considered to be a little bit challenging. Can you say why?
That image is more tilted. That image is more tilted.
Exactly. The pose. So this one is a little bit moved in this direction. So the pose of this view is different from the pose of this view. Okay? Can we still match them? The answer is yes, we still can match them. Okay? Can we match this? Actually, this is on top of the marsh. And the answer is yes, we can match it. Actually, yes, it has been matched. So we use you see those features? Match those. So we can use this information to find the match and to find the position of the robot on very unknown environment, just using rocks. Okay, so don't underestimate the rocks. Hopefully it's open now. It's still opening. Okay. So, in a simple way, all what we need to do is try to find features in some image and other features in the other image and try to find the criteria to match those together. This matching process will help us do infinite number of things. We can build panorama, we can localize ourselves in the environment, we can do a matching in unknown place, we can do so many things. But we have to be careful when we choose those features. Why? Because those features must have some criteria. What are those criteria? First, it must be an invariant. What is the meaning to be an invariant feature? Unique and not change with changing the pose and illumination. So it should be geometrical or geometric invariance, meaning it's against translation, rotation, and scaling, or it should be photometric invariance, meaning it should be against the change in brightness and exposure. Okay? If you can have the features that satisfy those two criteria, we are finding the best feature of all things. Is it easy to find them? The answer is no. Actually, scientists still searching until the moment for those features. I think look here. Oh yeah, this one. Will take a couple of minutes to load. Yeah, my computer is not powerful enough for this. Here we go. So here is the scene. As you can see, every red point is a corner. And when there is a green line next to it, this means that this corner is moving, or you are moving in the direction and the corner is moving back. Okay? Based on that, I can estimate the trajectory of movement. So now as you can see it moving straight, keep going straight, 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 straight. Then it will do U-turn. Okay, so this trajectory is estimated only from those corners and trajectory for the corners. That's it. Okay. This algorithm or this type of algorithm is very useful if you are completely disconnected from any other devices. So no GPS, no contact with cell phone towers, and you want to find the path for yourself. You started from where? You are going into the correct direction or no? Okay? That's what we call odometry. If you have or you are building a map while you are moving, in this case, we are generating another version from this, which called SLAM, simultaneous localization and mapping, which is actually, we cover in more details in the autonomous vehicles course. Okay. Anyway, so long story short, our goal is to find those points of interest our goal is to find those points of interest and find the features around. So this is the point of interest, this is point of interest, point of interest, point of interest, and the area around them are the features I'm looking for. Okay? Based on that, I can make matching between this and this. I can do all the operations we already discussed. Okay? Now, one of the important characteristic of those features that it need to be local. What is the meaning of local? Meaning it's inside the object itself. So it's not related to the environment. So it's not something, and it should be invariant as much as we can. So the locality will make it more robust to occlusion and clutter as much as we can, of course. Okay. The quantity need to be a lot. So having 3 or 4 features per image is not the thing we want. We want thousands and thousands, okay? Which is divided, or the scientists for this part divided into 2 categories. Some of them call this large number of features the blessing of dimensionality. Meaning I'm generating higher dimension or more feature that can give me more information. Another group say the curse of dimensionality. So having or generating large number of feature is a problem, is a drawback. Okay? And we always struggle between both of them, both branches. The branch that say yes and the branch that say no. Okay? But there is a technique actually that we can convert the higher dimension to low. That we will cover in a while, which called dimension reduction. So if you generate large number of feature, it's not a curse. You still can reduce this number of feature using the dimension reduction technique. Okay? So having low number of feature is the actual problem. Okay? One of them, or one scientist give this example. Assume that you have image for somebody face. Is it better to have it with a background with all details of ears and body and all the information and you extract it? Or it's better to have the image only for this area? Which is better? To have this whole entire scene and you extract it, or to give you only this small area?
Sorry.
Exactly. So having the big entire scene and you work with it however you would like, is much better and more flexible for you. Okay? If you only, all right, if I only give you this area, then you will be tightened. This is the only information that you have. Okay? So the high dimensionality is not a big problem. We always can work with this challenge. The second important thing, distinctive, means difference. So the features that I'm selecting must be distinguished for specific object. So here as an example, selecting this area considered to be unique because this gives me information about the type of tire and the type of cover and the upper area for this car. So I can easily use this in the matching process. Okay? On the other hand, if I choose the glass, is there any information on the glass? Not really. There's no information. So I can use it for matching. It can be available for all the cars, similar shape. Okay? So this way of choosing the feature considered to be an efficient, or sorry, an important technique or an important way to select our feature. And finally, I should be able to do this process in real time as much as I can. Meaning that, as you can see, when I run the algorithm now on my computer, how long does it take to start? Right? But when it starts to run, it runs with a decent power. Okay? So the number of frames per second, I'm working now on my machine, let's say about 10 to 15 frames per second, which is acceptable. But if your device can run it with 1 frame per second, this is not acceptable. If you want to work with a real-time constraint, this means that you need to run at least 15 frames per second. Some people put it up to 30. Meaning that your device must be able to process 30 frames in less than 1 second. Meaning that the number of features that we are generating must be too fast, as fast as possible. Okay? So those are the criteria or the advantage of using the local feature. I can always try to find something that runs in real time. I can always try to find something different in my object. I can generate lots and lots of features in the object, and I can make sure that they are in the object itself and robust against those changes. If I can do that, then voila, we can approach, or we can do all the goals we want to achieve. Okay. Okay. Now, what exactly we will do right now? We'll start to learn how can we generate the points of interest, which is considered to be the detection process. Where are the points of interest that I have in our image? Then, for all those points of interest, I will start to generate features around them. Those features will be called descriptors. I will try to make matching between those descriptors I generate for image number 1 and another image. And based on this matching, I can make the task I want to achieve, either for aligning, for 3D mapping, for whatever the task that I want to do. Okay? So let's start by the first type of feature. As we stated, we have 2 types of features or points of interest that we will focus on. The first one is the corner. The second one is blobs. So we'll start first by the corner. how we can identify the corner. Assume that I have image. This is an image. And I want to find the corner in this image. How exactly I can find it? They said, let's consider that we have a window, small window, of any size you would like. Then I will shift this window in all directions, even diagonally. So I'll start by one shift at a time. So I will shift it horizontally. So this is the original one, and I shift it this way. Now, if I subtract the new window from the old one, is there any difference? No. This one is gray. If I shift it this way, I take another snippet, this will be also gray. So this minus this result in 0. Try to shift up. Will be any change? Try to shift down. Diagonal. No. So under all the shifting condition, no change. So I will consider this area as flat area. It has no change. If I move this direction, this direction, this direction, this direction, try to subtract the new value from the old value, no change. That means it's a flat. If it's a blob, this means this is the blob. See the blob? It's something, has something surrounding it. Okay? And this means if you shift a little bit, you will find change. Right? Here, if you shift, you find any change? That's why it's considered as a flat area. Keep shifting until you arrive to this point. Okay? Now, at this position, if you shift it up or down, will you see any change in the value? Again, what I'm doing right now, I'm cutting the older position and subtract it from the new position and see if there is any change. If I shift it up and down, do you have any change? No. But if you move it left or right, you will find change or no? In this case, this is a line. So the line can be detected in this case if there is a change in one direction, not on the second. Okay? How about if the line is this way? In this case, if you shift left and right, no change. If you shift up and down, there will be change. Okay? So for both directions, the change only in one direction. Left or right or up or down. In this case, the change will be in the diagonal direction. Okay? If I'm in an area, if I shift up or down or shift or right or left or diagonally, and I find changes in all directions, they said in this case it's a corner. Okay? So the corner can be considered as the difference between two windows, or the difference between two windows that produce the maximum difference in all directions. Line will produce maximum difference in only one direction. If no difference at all, then it's what? Flat. Is this concept clear? No change at all, it's a flat. Change in one direction, whatever this direction is, it's a line. Change in every direction, it's a curve. Agree? Okay. Now we want to put this in a math. How can we do that? Listen, simply, I will consider a window at some initial location. Then I will shift it to a new location. I will subtract each pixel here from each pixel here and sum this error. That's what we did, or that's what we discussed 1 minute ago, right? So we'll do this with math. So I will start with this window at this initial position. Then I will shift with the value u and v. U in the x direction, v on the y direction. So I will have a newer image or a newer window, which called I of x plus u, y plus v. So this is the original, and this is the shifted. And subtract this from this, pixel by pixel. Because both of them are the same size, right? So this will give me the error at each pixel position. I will sum all of this. Not only sum it, by some square of it. Why? To maximize the error. If you square the error, you are maximizing it. If it's a small, you are making it bigger. So it will be sensitive. Then I will sum over all the x and y. Now, if this error is large in all directions, this means that we have a corner. If it's 0, we have no corner. If it's large in one direction and smaller in other directions, then it's a line. Okay? Are we agree with that? Now, can we work with this equation? The answer is yes. But in this formula, it's a little bit tricky. We need to approximate it a little bit or simplify it. Can we do that? They said yes. How? They said, let's go back a little bit in math. We will use something called Taylor expansion. Does this expansion ring any bells?
Camera brand,
Of that?
like a camera, there's cameras called Taylor.
Actually, it's a calculus. So this is included, or I'm not sure if you covered or studied in one of your advanced calculus courses. Okay, so Taylor expansion said that any function can be approximated around some specific points using polynomial, using polynomials. So whatever the function that you are working on, you can approximate this function around some specific point using polynomials. So the sum of those polynomials will reproduce your original function. That's exactly what they are trying to do using the Taylor expansion here for the image, but on a 2D, rather than working with the 1D for the regular function. Okay, we will continue this part next time, next week. Okay. Any questions? Sorry?
Multiple windows. Like we're doing single door.
Here, can we have multiple windows that you're saying?
Yeah.
Yes.
Okay.
It doesn't matter how many windows you are working with, but what you are doing is calculate the shift by each one. Okay. So what we are talking about is parallelizing the process.
Yep.